All right, let's talk about the compound interest and the continuous compound interest. All right, so I'm pretty sure the formula is somewhat familiar to you guys. A of t is equal to, so it's amount in your bank account after t years, basically. Principal P, initial investment, times quantity 1 plus annual interest rate divided by the number of compounding periods per year, raise it to the nt. T is time in years. All right. So, for example, if the interest is compounded, say, monthly, right? If you have monthly, then this means that n is going to be equal to 12 because interest is compounded 12 times a year. All right, then if it's a quarterly, then n equals 4. Semi-annually, means n equals 2. And annually means that the n equals 1. All right? Or you can have, interest compounded daily or weekly, or, so say daily. Then if there are 365 days, so n equals 365, right? And so on. All right. Then you might wonder, what if interest is compounded like every minute or every fraction of minutes or every seconds, right? What would happen to the interest or the formula, right? So what we do is we're going to make this a number of compounding periods per year as big as possible, or make it bigger and bigger, right? So then we have to think about, okay, maybe we can take the limit. So for big N, so we can just say, I'm going to just take the limit of this compound interest formula, right? Then send n to, say, infinity, right? What would happen to this, right? So which means that the interest is compounded continuously, right? So let's look at this, right? And remember that the definition of E, which looks like this, right? So I'm going to try to mimic this definition since I know that E is, exponential function is involved here. All right, so we're going to do this substitution. So we want to have 1 plus h. So I'm going to let this guy equal to h, right? And as you can see that as n approaches infinity, h approaches, right? H is r over n, so r is a fixed number, and n is getting larger and larger, so h is actually approaching 0, right? So keep that in mind. All right, so this is going to be, so by using a substitution, we can think of it as limit, right? So p is a constant, we don't have to change that, and the 1 plus, we decided to call that guy h, right? So you have h is equal to r over n. So we can rewrite n as r over h, right? So here n is r over h. So you have r over h t, right? Then since as n approaches infinity, h approaches 0, so instead of n, I'm going to say h approaches 0. All right, then we're gonna, since we have 1 plus h, then you have a 1 over h power, which is exactly the definition of E. So we're gonna separate that. So one thing is p has nothing to do with the h, so we can put it outside of the limit, and the limit as h approaches 0. Then you would have 1 plus h, then you have a 1 over h, so I'm gonna just go ahead and do that, right? Then I'm going to go ahead and take the limit, but we still have to raise it to the RT power. So we're gonna just raise it to the RT power after we take the limit. So go ahead and take the limit. We're gonna raise it to RT later. Right? Now we can see that this is exactly the definition of E. So therefore we have P times E to the RT. Right? So that's where they got the continuous compound interest formula, which is P times E to the RT. Right? So that's how we got the continuous function. It was just taking a limit of the compound interest formula as n approaches infinity. That will give us the formula for the continuous compound interest. Right? That's it. So now we know that where this E came from. Right? That's it. I hope that this was clear.